Hello chemists, welcome to Lecture 1, Chemistry Essentials. In this lecture video, we will talk about the significance of chemistry and hopefully answer the question of why you're here taking this class this semester. So let's get started. So remember, the first thing that you need to do before watching these videos is download the lecture slides. So to do that, you'll want to go to Canvas, go to our class, and then head to Modules. All right, and then since we're in week 1, you'll head to the Lecture 1 Chemistry Essentials and then download the slides. Ooh, I should have done this beforehand. Okay, so there are the slides. So you can either print them out on paper or send them to Notability. Create a new note since it's a new set of slides, or organize it however you wish. I'm going to send it there into my subject of Chemistry 1210 and import, and then head on to Notability to start the lecture. All right, Lecture 1. So, like I said, I'm going to be talking about the significance of chemistry and talk about why you're taking this class. Well, chemistry surrounds all of us. Chemistry is involved in everything that we touch, we see, we feel, we taste. It's all because of chemistry. And I think in this day and age, there's a lot of what I call, or what people call, chemophobia, where people are afraid of the word chemicals, or they think that all chemicals are bad, but that's just not the case. As you learn more about chemistry and the properties and structures of chemicals, we'll learn about what makes chemicals dangerous and what makes a specific chemical necessary for us to live. So the main point here when talking about chemophobia is that nothing is chemical free. Like in the previous line here, everything we touch, see, feel, taste is all because of chemistry and chemicals. So oftentimes chemistry is called the central science because it is a fundamental principle of all sciences. So you see here in this schematic that look, chemistry is in the middle, so obviously a chemist drew up this diagram. So chemistry is in the middle, and it's connected to all of these different other STEM fields. So obviously chemical engineering, nuclear chemistry, all deal with chemistry, but also some things you might not think about, like if you've ever taken a physics class or a geology class. Agriculture and food sciences relies heavily on chemistry. One of my hobbies, when I'm not in lab or teaching, lecturing chemistry, is cooking. Cooking food science has a lot to do with chemistry, and having a better understanding of chemical reactions and chemistry fundamentals can make you a better chef. Other STEM fields that are related to chemistry, biology and medicine, and etc. Let's do a thought experiment and think about some household chemicals that we use on a day-to-day basis. So something off the top of my head, something like bleach. Bleach, you and I use bleach to whiten our whites before we put them into the laundry. But you and I know if you were to ingest bleach, especially a lot of it, it would be very detrimental on our bodies. That's why there are those safety caps on things like household bleach. Something else along those lines is like alcohol, rubbing alcohol, hand sanitizer. We utilize the properties of alcohol to disinfect our surfaces and hands to keep them germ-free. But we also know if you were to ingest alcohol in excess amounts, that there is an effect on the body. Maybe you would consider that detrimental. So both of those things are chemicals that aren't so great for your body. So let's think of some other things that are also considered chemicals that, aren't as bad sounding as bleach and alcohol. Things like vinegar. Vinegar, when you smell vinegar, that distinctive smell is actually the chemical acetic acid. So you can think of vinegar as an acid. So if you make a salad dressing or you make pickles or something, you are utilizing the chemical acetic acid in when you use vinegar. Also things like baking soda. So essentially anything in the kitchen, food related, you're utilizing chemicals, and food is good, so it can't be that all chemicals are bad. I just want to get that misconception out of the way. So Vinegar is acetic acid. Baking soda is sodium bicarbonate, which is the chemical name for it, but we just call it baking soda. Some other things that you might not have thought of that are also chemicals, something like plastic is a chemical. Plastic is composed of small linkages of chemicals all bonded together to make what is called a polymer. And because they're all chained together, plastic can be rigid and strong at the same time. And it can also be molded into a lot of different shapes. Um, Things like bread. I was just making bread the other day. Bread also contains chemicals like gluten and carbohydrates, which give it its characteristic deliciousness and nutrition. Things like meat has a lot of proteins. Protein is also a chemical that has certain properties that give meat its characteristic tastes. Uh, Something like juice has a ton of sugar in it, which makes it tasty for us. Sugar is also a chemical that we will learn about later this year. And then juice also contains water. Water is one of the most basic, fundamental substances on this earth, and it is also considered a chemical. So essentially, you can just write down absolutely anything that you can touch and hold on this slide, and that would be a chemical, essentially. Anything that you can touch, feel, taste, smell, all those things are chemicals, technically. So let's get that misconception out of the way. Are chemicals good or bad? Well, it depends what the structure of the chemical is, what properties it has, but definitely when people say, oh, all chemicals are bad, that's just plain wrong. Or if you see on packaging something says, oh, chemical free water or something, that is completely false. There's no such thing as chemical free water because water in itself is a chemical. So if it was chemical free, there would have to be nothing in it, not even air. Air that we breathe also contains chemicals in it. The oxygen that's in it that we need to survive, carbon dioxide and nitrogen, that is the majority of air. All of those things are chemicals. So if you had a container that was that contained chemical free substance on the inside, there would literally have to be nothing. It'd have to be a vacuum on the inside for it to be chemical free. So applying this to things like food packaging and stuff, when I just want you to have a discerning eye when you read food or, package labeling. When they talk about natural and organic things, all those things, natural and organic, have different meanings. So on this slide, I say, so essentially, when something's natural or organic, it just means that there's no synthetic additives to the substance. So, like if I said I had organic or natural corn, essentially what that means is that, nature grew the corn with chemicals. Corn contains chemicals, right? But we did not add anything in addition to what nature added to it. So things like organic foods, they cannot be processed using irradiation or solvents or additives because that would add non-natural chemicals to the produce. Um, and also, there's a difference between natural and organic. Organic has a more defined definition, while the FDA actually has no standard definition for the term natural. So always have a discerning eye when you see something like natural chicken versus organic chicken. I mean, all chicken is typically natural because they come from natural sources of, living chickens. So all chicken should be natural unless it was lab made, like made in a petri dish or something. But the difference in price would be organic chicken versus non-organic chicken, or just regular chicken, because organic chicken has the definition of cannot be processed using these things, irradiation, solvents, or food additives. So I just want you guys to be thinking about those things when you're doing your shopping. All right, and then again, I say nothing is chemical free. So water is a chemical, air is a chemical. Things like tap water, spring water, and mineral water. All of those things are full of chemicals. Additional chemicals that are there naturally, like if you have hard water. That means you have extra calcium and magnesium in your water in addition to H2O, which is the chemical formula for water. So, again, if you see something that says, oh, chemical free, that is absolutely wrong. Everything contains chemicals. All right. So again, we're kind of trying to answer the question of why are you here? Well, it's because chemistry surrounds you. Everything we touch, see, feel, taste, everything's made of chemicals and nothing is chemical free. Right? So that means that we're just learning about the world around us because this whole world, we're just made of chemicals. So hopefully, with this whole course, you can learn a little bit more about the world around you through the lens of a chemist. So we'll be thinking about things in terms of chemical formulas, chemical structures, things like that. When you see cool demonstrations on the internet or in class or something, sometimes students, they're amazed at these chemical reactions, and they're like, oh, this is like magic. No, it is not magic. So chemistry is not magic. Everything can be explained by using chemistry and fundamental principles. I like to joke about as you learn more about chemistry and physics and all these things, all those principles, you'll start to learn that these demonstrations aren't magic, and we just kind of the professors, we kind of ruin it for you. We ruin the illusion that we can do magic. It's not magic. It's all explainable, and we kind of ruin the fun when we unveil behind the curtain and you see the reason why these things actually happen. So hopefully, I can ruin some chemistry demonstrations for you this year. All right, so let's actually get into some definitions and writing on these lecture slides. So chemistry. We already talked about how chemistry is the central science when it comes to the STEM field. And this field studies the composition, structure, properties, and reactions of matter. So what do I mean by composition, structure, properties, and reactions? Well, all of these things can describe the piece of matter that you're studying. So what I mean by composition is the composition of matter is what is this matter made out of? What is it made of? Are there oxygens present? Are there hydrogens, nitrogens present? Is it made of metals, transition metals, heavy metals, things like that? Then you can ask yourself about a piece of matter, what is the structure of this matter? So essentially, you're asking yourself, how is the piece of matter put together? Because that is very important. Put together. That is very important to chemists because you can have oxygens, hydrogens, carbons put together in different types of arrangements, and you can get completely different characteristics out. Other questions that we can ask ourselves is, what is the property of this matter? So essentially, you're asking, what characteristics does this piece of matter have? What characteristics does it have? So, is this piece of matter, is it hard? Is it brittle? Is it shiny? Does it melt easily? Is it a liquid? Is it a solid? Is it a gas? All those are based on properties of that matter. And then lastly, we can talk about reactions of matter. So essentially that means, how does this specific piece of matter behave with other substances? So we know if we combine oxygen with iron, you can get something like rust. So that is a reaction property of iron. All right. So we've talked about how the definition of chemistry. Chemistry is the central science that studies composition, structure, properties, and reactions of matter. So what is matter? Well, matter is very simply all the stuff that makes up the world. So anything that you can touch, see, hold, smell, taste, all of that is matter. And then let's also define chemical while we're at it. A chemical is just any substance or matter that has the same composition, structure, properties, proper properties no matter where or how it is found. So for example, water. Water, regardless if you find it in the ocean, in a puddle outside your house, in the sky, water, in the sewers, as long as it's water, it will always have the chemical structure H2O, meaning it will have the same composition H2O no matter where you find it. It'll also have the same structure and properties no matter where you find it. All right. So let's keep thinking about chemicals in terms of our day-to-day uses. So here I have an example of different chemicals off of the ingredients label of toothpaste, which is just a simple mixture. We'll talk about mixtures in the next lecture slides. So here are some of the ingredients. So the active ingredients in this particular brand of toothpaste, which Tom's of Maine, that's a pretty natural toothpaste brand. So you would think, oh, Tom's toothpaste probably has less chemicals than, I don't know, Colgate, but that's not actually the case. What you'll see here, there's tons of different chemicals in this toothpaste. So you see sodium fluoride, which is an anti-cavity agent. That's the active ingredient in Tom's toothpaste. Some other ingredients in this toothpaste includes water, sorbitol, silica, xylitol, glycerin, sodium chloride. You probably have never heard of any of those chemicals except water and maybe sodium chloride. And that's all in this natural brand of toothpaste. But every single one of these chemicals that's inside this toothpaste has a specific purpose. So that is why it is there. Typically, manufacturers don't add things to a product unless it's needed. So each of these things has a certain purpose. A lot of these things that I said, sorbitol, xylitol, those things are sugars. So when you're brushing your teeth, it's a more pleasant experience. Water, hydrated silica, those things give it the texture of toothpaste. So again, just have a discerning eye. Tom's toothpaste is more of a natural brand, but that doesn't mean that it's chemical free. There's still substances in this toothpaste that you probably have never heard of, but none of these things are really out of the ordinary as I read it. All of them have a specific purpose. And I think, yeah, on the next slide, I actually have some of the different structures of all of these things. So water has the chemical structure of H2O that looks like that. All right, this is sorbitol. Here's hydrated silica, xylitol. I think this is glycerin. I think I skipped a few. This is sodium lauryl sulfate. All soaps have sodium lauryl sulfate in it, and it looks like this. So we cannot say that this natural toothpaste is chemical free. It definitely contains chemicals, right? And here's another example. So an egg. An egg is as natural as food comes. It comes straight from the animal source. But this is if there was actually ingredients printed on an egg, these are the different chemicals that are found in an egg. So things aqua, that's just water. I don't know why they write it like that. So the majority of an egg is water. So it's about 3/4 water. But that other 25% of an egg, it contains amino acids, fatty acids, sugars, different colorings and flavors. And so here I have a whole bunch of the structures of all of the different chemicals that are in an egg. So you would think that, an egg is as natural as it comes when we're talking about food sources. But in fact, there are chemicals inside eggs. So if you haven't gotten it yet in these first 7 slides of this lecture, is that everything contains chemicals. absolutely everything. And that's really important, especially to what you are studying now and in your major and your future career. Understanding that everything contains chemicals, everything can be explained using fundamental principles will be really important as you move forward in your career, in your academic career and your lifelong careers. I took a look at the class roster, and I have here a list of all the different majors that are represented in this class. So we have a lot of pre-health, nursing, and dental folks. You guys in the health sciences will definitely be using a lot of chemistry in your future careers. You know, any ointments and creams or drugs that you'll administer to a patient all has to deal with chemistry and the composition, structure, properties, and reactivity all have to do with the drug that you administer to a patient. The folks in the environmental science and agriculture fields, you guys are definitely going to deal with how chemicals manifest themselves in nature. You know, how can we dispose of some of our more toxic wastes in safe ways that aren't detrimental to ourselves and the ecosystem? Folks in radiology and therapy also will deal with chemistry when rehabilitating patients. And then, obviously, the education field, you'll have to teach chemistry in some capacity, just like me. So this is the map of chemistry. I really like this picture because it's a really pretty way to represent chemistry in its full glory. So on this green side, this is all the rules of chemistry. So all the guiding principles that we will learn this semester. So things like types of reactions, different phases, types of energy, chemical compounds, the origins, which is really the alchemy that we'll actually talk about in this lecture. See here we have matter, the structure of an atom. So things like that. All of these are all the rules and principles of chemistry that we can apply to technologies to create new different applications that can better enrich our lives. So that kind of brings us to this yellow side, different types of chemistry. So it's essentially taking all of these principles and applying it in different ways, and this gives us our areas of chemistry. There's physical chemistry, inorganic chemistry. That's what I deal with, inorganic chemistry, because there's a lot of pretty colors in inorganic chemistry. Really, that's honestly why I decided to study inorganic chemistry. Things like analytical chemistry, biochemistry, organic chemistry. All of these different chemistries, it's all considered chemistry, but they just use different sets. They just concentrate on different sections of these principles that I just talked about. So let's make sure everyone out there is listening with this learning check. So, which of the following examples contains chemicals? So, which one of these examples is matter? So, remember, matter is everything that makes up the world around us. So, fertilizer, yep, contains chemicals. So, you agricultural folks, fertilizer is in fact a chemical that you will work with in your future careers. Vitamins. I can hold a vitamin. I take it, and hopefully those vitamins nourish my bodies, in addition to the things that I eat. So vitamins also contains chemicals. What about sunshine? This one's a tricky. So can you hold sunshine? No, I can't put it in a bottle. I can't carry it around with me. So sunshine is not a chemical. It's Sunshine is made of light, which I think we will talk about later in this semester. It's not a chemical, but we do deal with light as a form of energy. Iron nails. Well, yeah, I can hold an iron nail. I was just putting together some furniture from IKEA, and I was holding that nail really steadily before I was hammering. That contains chemicals. Paint. Yeah, I just painted the whole first floor of my house this summer. Yes, that is a chemical or contains chemicals. Happiness. Can you hold happiness? Can you put it in a jar? No, no. Happiness, unfortunately, is not a chemical. So hopefully we went through that learning check and you got all of those things. So let's keep going. So let's talk about the origins of chemistry, which is alchemy. So if you look back at that map of chemistry, that I showed you earlier, you can see, in ancient times, alchemy is really the origins of chemistry. A lot of the processes that we use in chemistry date back to alchemy. So, in ancient times, alchemy dealt with four different elements. These four elements are different than our much larger periodic table of elements. So they only dealt with four, and they believed that these four elements comprised all of matter in nature and in their world. So these four elements include water, wind, earth, and fire. So if you ever watched the TV series Avatar: The Last Airbender, that's where they get all of the four elements, the four nations. I highly recommend that series if you have time. So those four elements and the four qualities that correspond to those. So here we have hot, dry, cold, and moist. So if we combine the elements and their qualities, we get this diagram, which is Aristotle's diagram for the four elements. So you can see the four elements are in the quarter: air, fire, water, earth. And so essentially what they believed is if you combined two of the qualities on either side, hot and dry, you will get fire, right? If you combine hot and moist, then you'll get air. If you combine moist and cold, you get water, and if you combine cold and dry, you get earth. Now, if you wanted to go to change a substance that had a fire element to an air element, what they believed is all you had to do was change its hotness. So if you remove hot from fire, you get air, right? If you add more moisture from air, if you add more moisture, you get water. So they believe that you could transmute substances, change their properties, change their composition using this diagram. And the whole point of this was to be able to manipulate metals to make gold. The whole goal of alchemy was to make the precious metal gold. So that's why they had this. If you manipulate substances, you can transmute them to gold. So that was their whole goal. Obviously, they failed at doing this, but in the process, they made a lot of contributions to science, which we talk about in this slide. So alchemy, they were constantly trying to make gold using these principles of the elements and their qualities and changing them to make the substance that they wanted. So their contributions to science is they were able, in order to reproduce different experiments to try to change one substance to another, they made observations and they collected data and they wrote them down. The next person could reproduce those experiments and try to make the same substance. They also developed different lab equipment to do these experiments and different procedures, so they could repeat them. So the apprentice could learn from the master and learn these different techniques to change substances. Other contributions that they made or added to, so medicinal herbs. Medicinal herbs was an important thing to alchemists. They realized the importance of herbs and how those chemicals can be beneficial to human society. And in the end, they always were balancing things, by weight, because that was one of the things that they actually could measure was weight. So, they would take a substance, they'd weigh it, they'd burn it, and then they'd weigh it after. So a lot of their experiments were about balancing and unbalancing and rebalancing these reactions to make sure it all fit. And a lot of these procedures is what science is all about. So we really have alchemists and their quest to make gold to thank for the science that you and I use today. All right, and so we have this quote: "All things are poison, and nothing is without poison. Only the dose permits something not to be poisonous." So that's really insightful. I think of water as an example here, because water is really essential to our bodies, but too much water is poison. It's all about dosage. Yeah. So a quick side story. I'm too young for this, but the chemical that they use for Botox procedures that celebrities use, Botox, the chemical that they use for that is actually the most toxic substance known to man, by weight. So just a tiny bit of it can kill you. But in a tiny, tiny, tiny microdose is beneficial to the celebrities who want Botox and they want a, younger looking face. So it's all about dosage. And that's what Paracelsus, the founder of toxicology, really pushed. We specifically have Paracelsus to thank for our modern day chemistry. So here is his picture and his full name. He was the founder of toxicology, which brings us back to that quote that we had in that previous slide where he said that dosage is really important for determining whether a substance is, essential or beneficial to the human body or detrimental or poisonous. He also studied psychology and recognized that diseases don't have to stem from a malfunction of the physical body, but it can come from a mental state. He also was a big proponent of using observations in his studies, which is really important to us scientists. He also is credited with naming things like zinc and using terms that you and I use on a day-to-day basis, like gas, alcohol, and chemistry. So let's thank Paracelsus. All right. And so Ohio State University also has a tribute to alchemy. So this building is on main campus in Columbus, Ohio. This is the McPherson Laboratory building. This is actually where I did my studies as a PhD graduate student. So these aren't the doors that I would go in every day, but I use these doors from time to time. So this is OSU's tribute to alchemy. It's actually right up here, what you want to look at. Through the threshold. So OSU's tribute to alchemy, they have all the different element symbols there up top, which I think is pretty neat. So we've talked about ancient applications of chemistry through alchemy, but a lot of history and chemistry, they really go hand in hand with one another. A lot of historical events were actually shaped by chemistry. Wars were fought over materials that were only specific to certain regions of the world, and wars were won by nations who could understand the chemistry and technology used to fight and ultimately win wars. So I like to give an example of an historical event that we all know, the American Revolutionary War, but let's look at it through the lens of a chemist. So understand during this time period, during the Revolutionary War in the 1700s, this war was fought with muskets, which is a type of gun that requires gunpowder to be put down the barrel of the gun to propel the bullet forward. So gunpowder has three different components to it. So they mix these solid components together: sulfur, carbon, and saltpeter. So sulfur and carbon, right off the periodic table. Saltpeter is the common name for what we now know as potassium nitrate, or KNO3, which I have right here. So a little bit about these three components. Sulfur was very easy to find. There were huge sulfur deposits in Italy. You could heat rocks really, really hot and actually get pure sulfur to sublime out. Carbon, also easy to find. That's coal. Right? Pure carbon, or semi-pure carbon is coal. It was the saltpeter that was hard to find. So this KNO3, isolating this compound was near impossible during this time. And so they only had natural sources for it, and they could only find it in caves where things were decaying. And modern gunpowder is about 75% saltpeter. So really, if you're a country in wartime, you need a lot of saltpeter to make that gunpowder. So whoever has the most saltpeter, has the most gunpowder, is probably most likely to win the war. So this summer, I became a fanatic about the American sensation Hamilton the musical by Lin-Manuel Miranda. So when I watched this musical, I couldn't help myself but think about this musical through the lens of a chemist, particularly during this one scene. So let's just take 2 minutes and watch this scene, and then I'll break it down for you what I was thinking about this scene as a chemist.
How does a ragtag volunteer army in need of a shower somehow defeat a global superpower? How do we emerge victorious from the quagmire, leave the battlefield waving Betsy Ross's flag higher? Yo, turns out we have a secret weapon, an immigrant you know and love who's unafraid to step in. He's constantly confusing, confounding the British henchmen. Everyone give it up for America's favorite fighting Frenchman! Taking this horse by the reins, making red coats, whether we blow stains. and so their balance shifts.
We rendezvous with Rochambeau, consolidate their gifts.
We can end this war at Yorktown, cut them off at sea, but for this to succeed, there is someone else we need.
I know.
So he knows what to do in a trench, ingenuity, they're fluent in French, I mean. So you're gonna have to use him eventually, what's he gonna do on the bench, I mean. No one has more resilience or matches my practical, tactical brilliance. You want to fight for your land back?
I need my right-hand man back.
Yes, get your right-hand man back. You know you gotta get your right-hand man back. I mean, you gotta put the button to the letter, but the sooner the better to get your right-hand man back.
Alexander Hamilton, troops are waiting in the field for you. If you join us right now, together we can turn the tide. Oh, Alexander Hamilton, I have soldiers that will yield for you. If we manage to get this right, they'll surrender by early light. The world will never be the same. Alexander.
So I hope you don't mind watching that short little 2-minute clip so I can finish my history and chemistry story. So I wanted you to focus on the first half of that musical number, where Aaron Burr introduced General Lafayette. Lafayette was a French citizen fighting for the Americans during the Revolutionary War. If you haven't seen the musical, I highly recommend it. So hopefully I didn't spoil it for you. Anyway, so what you should focus on here is that the French and American relationship during the Revolutionary War was very important. It was actually that alliance between the French and Americans that really helped us win the war, and it all has to come down to gunpowder and saltpeter. Because the French actually perfected the isolation and synthesis of saltpeter from manure and urine. So remember, before they could make it themselves, they had to either mine saltpeter, find it in nature, and it was very difficult. During this time period, there was a lot of wars going on, the 7 Years' War, lots of trade routes were cut off, so trading for saltpeter was very difficult, and of course, countries were hoarding it for their own army usages. So since the French were the first ones to essentially mass produce saltpeter, the main component of gunpowder, they essentially went from having the worst gunpowder in the world to the best gunpowder in the world. And so I think the statistic is that like 90% of all gunpowder used during the Revolutionary War on the American side came as a gift from France. And so when watching Hamilton, this musical number, they introduced Lafayette and hype him up so much, it just, all that made me think about was French gunpowder. I think the saying is that the American Revolutionary War was won by the urine of French dames, which just means that, the saltpeter or potassium nitrate that was in all of the muskets of the American soldiers came from the women in France from their urine, because that's how they made saltpeter. Let's think about chemistry in a broader context. Chemistry falls under the heading of science. Science subjects include chemistry, biology, physics, all of those things. So science essentially is just a way of making sense of the world. And in our science classes, we all use different approaches to explain the natural world. So in biology, you look at the world of the living. In chemistry, we look at the chemicals that exist in our world, and in physics, we look at the physical aspects of the world. So in all of those subjects, we observe the world through that specific lens, and in all of those subjects, we apply logical and rational approaches to explain the things that we see. All of the sciences have their own specific language. So since you're sitting in a chemistry course, we're going to be using chemistry terms to explain the chemical phenomena that we see. Also, all sciences use what's called the scientific method to scientific method of observations and experimentation to understand the natural world. So, what exactly is the scientific method? Well, we use the scientific method in our everyday life. We use it every day. We ask ourselves questions and we seek answers to organize that information to understand the world around us. And so the scientific method is based upon using empirical knowledge. So, what is empirical knowledge? Well, it is information that comes from observation and testing. We've seen this before. They used, observations and writing things down and testing, experimentation in the alchemy era. And we are still using those fundamental principles today and apply that to science and the scientific method. So, empirical knowledge, it's just information that we get from observation and testing. So, it's really about perceiving the world around us and sensing what is happening. And hopefully, we can take that information and explain more about the world around us. An example of the scientific method, us using it in our everyday lives. So, I have my pen right here that I'm holding up, right? What will happen if I let go of the pen? Well, we have enough experience in our lives to know that if I let go of this pen, that it will drop. So that is using the scientific method, using empirical knowledge through my observations, and testing. I'm going to test my pen and observe that it falls to the ground. So, more specifically, the general principles of the scientific method, or you can think of it as like problem solving, the steps to the scientific method. The first step is always to make observations. So that means we want to observe the things around us, we want to describe the things around us, and measure the things around us. So we're essentially just collecting data and facts. The second principle or second step to the scientific method is to write a hypothesis. The third is to perform experiments to test your hypothesis. Perform experiments. And finally, the last step to the scientific method is to propose a theory. And a theory is really just a more robust hypothesis. And of course, you need to continually test your theory, hopefully by different parties, to see if your theory holds true. Like I said before, we use problem solving every day to fix problems that we run into. And essentially what we're doing is applying the scientific method to these problem solving things. So I have an example here where I have an issue. I use my phone, I'm trying to log onto a web page and it won't load, right? Like let's say I'm trying to log into Facebook and the Facebook homepage won't load. So there are logical steps of observation and experiment that a typical person will go through to fix a problem like that. So if Facebook won't load on my phone, the first thing, I'm not going to email Mark Zuckerberg right away and say, hey, Facebook won't load, fix the problem. That's probably not the first thing that I'm going to do. So instead, we try to come up with easier experiments or trials to do to fix the problem. So, the web page won't load on my phone. What can I do? So maybe I might think, oh, maybe that website is down. Maybe Facebook just is shut down right now. So maybe the first experiment or trial that I do is just see if a different web page loads, like Google. Type in google.com on my web browser. Crap, it doesn't load either. So that's not the issue. So now I have to go back and think about something else that I can test. So I might think, oh, maybe I'm not connected to Wi-Fi. So I check the Wi-Fi settings on my phone, go ahead to, the settings, look at Wi-Fi. Oh, it looks like that I'm still connected to my home network, so that's not the issue. I might think, okay, maybe the router is down. Maybe I don't have internet connected to my home router. So the next experiment might be to check the router settings and perhaps restart it. Maybe restarting it will give that internet back. But let's say I do that, I restart the router, still no web page. So that's not the issue. So let's go back to the drawing board, do a different experiment. Okay, maybe it's my phone that's messed up, and maybe my phone's just like incorrectly connecting to the router. So maybe I'll log into a different device like my computer and see if my computer can load the Facebook web page. But I go to my computer, load it up, still no web page. So maybe it's the internet provider. Maybe I'm not getting any internet uh, to to my phone or to any of my devices. So maybe if I turn off all of my Wi-Fi off of my phone and just use my Verizon LTE network, use my mobile data to see if the web page loads. Lo and behold, if I turn off my Wi-Fi, the web page loads. So it must be with that experiment we've isolated that it's a Wi-Fi problem, not a website problem. So when I turn off my Wi-Fi and use data, I can see that Facebook works. So then maybe my last experiment to just really to determine what the problem is, maybe there's an outage, internet outage in my area. Like I have Spectrum, so check the Spectrum outage map using my data on my phone, and there it is. There's an outage in my area. Hopefully, the internet guys can fix it. So this example just shows you the steps of problem solving that we use in our everyday life, and this is essentially what the scientific method is. So let's go into a couple more definitions. So if we remember back to the four steps of the scientific method, the first was to make observations. So observe the things around us. I saw that my the web page wouldn't load on multiple devices, all those things. Those are making observations. Next is to write an hypothesis. So what is a hypothesis? Well, it is a statement that is that is proposed to explain a series of observations and relationship between these observations. When you write a hypothesis, it must be worded in such a way that you can test it by experimentation. So a lot of these observations that we made, we can make a hypothesis. So for example, like the first observation, a website on my phone won't load. So the first thought is maybe Facebook is the website is down. So Facebook website is down. That would be a hypothesis. Well, how do we test it? Well, we can check if other websites will load, or we can use a different device to see if Facebook will load. So that is a hypothesis that we come up with a observation. The observation is Facebook won't load on my phone. Our hypothesis is maybe the Facebook website is down. Right? And so hypotheses can be wrong. They're just educated guesses to explain these observations. So we saw that in that previous example. These are just educated guesses to see what the issue, what our problem is. And through experimentation, we can see whether that hypothesis is correct or wrong. So essentially, a hypothesis is just an idea to explain how or why something is happening the way it is happening. All right, so that is hypothesis. So we talked about how we can test hypotheses with experimentation. So what is an experiment? An experiment is just a test or multiple tests that determine the validity of a hypothesis. Usually many experiments. You can do many experiments to test a hypothesis, oftentimes by different scientists or investigators. So maybe, if you're with a friend and Facebook isn't working, you'll ask your friend, hey, can you see if this web page is loading for you? Those are just, normal problem solving things that we use in our everyday life. And scientists do the exact same thing. So that is an experiment. So our next definition is model. So essentially, when we have hypotheses, we generate these hypotheses, statements to explain the observations around us. Once you have enough hypotheses, you can express them using a model. So a model is a physical representation of what may be occurring. So a model doesn't necessarily have to be correct, just like with our hypotheses. As we do experiments, we might do experiments that, confirm the validity of our hypotheses, and our model might be correct, but all it takes is one experiment to, prove our hypothesis wrong. So I emphasize models may represent what is occurring because it can always change. Models can always change, and we'll learn about that in chemistry, that a lot of chemical models change as more information is observed about the world around us. So we use models every day to represent things around us, and some are more accurate than others. Sometimes we deliberately use inaccurate models. Essentially, models give us a picture of the hypothesis or concept that we're trying to explain. So one example I have is the Earth model. All right, so here's our Earth. Here's our Earth, the globe, right? And so the globe is a physical representation of Earth. So here's, a picture of the Earth that astronauts took a picture of, and a globe is the physical representation, probably the best representation of the Earth. The problem with the globe, though, is that I can't carry the globe, in my pocket. If I need to reference the Earth somehow, I'm not going to carry a globe in my pocket. So oftentimes in textbooks, you can't put a globe in a textbook. So there are other Earth models, including the globe. And these are, the flattened map projections of the Earth. And there's actually, with Earth models and map projections, there's also multiple different Earth projections that we have. Like I said before about models, models only may represent what is occurring. So this Mercator projection, the one that we see mostly in textbooks, is actually kind of incorrect. And it has to do with the relative sizes of the land masses. Because the problem is we're taking a spherical globe and flattening it out on a flat surface, so that you get some distortion there. So what you see here in the Mercator projection is that Greenland is basically the same size as Africa, but that is incorrect. So map people came up with a different representation of the world, and that led us to the Gall-Peters projection, which is actually a more accurate representation of the relative sizes of the different land masses. So what you see here is that Greenland is actually much smaller than Africa, but we don't typically see this specific projection in textbooks because it looks very distorted. But again, that's the problem with taking a spherical globe and putting it into a flat 2D rendering. And so to combat that problem of the distortion, the final projection that is kind of takes the pros of both projections is the Robinson projection, where the land masses are in fact more accurate to the globe. So here you see Greenland is in fact a lot smaller than Africa. So this example, these three different projections, just kind of highlights that models may not be correct. It's just our best physical representation of what we believe is true, and that models can change as more information is gathered. So here are also some more examples of models. So again, models are just physical representations of what is occurring. So here I have an American Girl doll. She is a physical representation of a small child. Here I have an action figure who is the physical representation of the Man of Steel himself. Here's another model. The model's right here, this plushy doll. That is a physical representation of Grumpy Cat. That's another example of the model. And probably the most well-known model is Barbie herself, which is just the physical representation of a adult woman. The problem with Barbie is that she isn't a accurate representation of the female body, which is fine. I mean, models are just representations. They aren't necessarily always correct. So if we take a closer look at the Barbie model, if we took an actual Barbie, like the proportions of a Barbie, and blew it up to an actual human scale to make it resemble what it's trying to model, if Barbie were an actual woman of like lifelike size, she would be 5'9", 5 feet 9 inches, and 110 pounds. All right, her neck would be too small to support the weight of her head, so I guess her head would just be like floppy, right? And because of the proportions, she would have to walk on all four, her legs and her legs and her arms in order to support her whole body. So Barbie, as we know, is not a perfect representation of the human body. So here I have an example of what Barbie would have to look like if she was actually properly proportioned to an actual human. So this is the original Barbie, right, with the incorrect proportions. A Barbie doll that actually resembled or reflected the actual human body anatomy would look more like this. So I showed you a couple examples of models that we come across in our everyday life, like dolls, map projections, and the globe to represent things around us. But in a chemistry course, we use different kind of models. So models that we will study later in this year includes the atomic model. And so you see here I have a couple examples of atomic models, and actually these models changed as time went on. We started here with Dalton's billiard ball model. This is what chemists thought that atoms were, that they were just these, hard spherical balls. But as more information came in, as we did more experiments, made more observations, we had to change that model to fit what we were actually seeing. And so you see as time went on, the model for the atom became more specific. It changed, and now accurately represents what an atom is. This model. So we'll go more into these details later in the year. All right. So finally, the last step of the scientific method is to propose a theory. So how do we go from hypothesis an experiment? How do we go back and forth between those? How does a hypothesis become a theory? Well, hypotheses need to be tested repeatedly with lots of different experiments and hopefully by a lot of different people. So after a lot of experiments are made, as long as the hypothesis is not disproven, because all it takes is one experiment to change a model, to essentially nullify the hypothesis. As long as the hypothesis isn't disproven, eventually the scientific community accepts the hypothesis and it becomes a theory. So there's kind of a gray area between hypothesis and theory. It essentially has to be accepted by the scientific community that this is true. But again, theories can change because all it takes is one experiment to disprove the whole thing. So essentially, a theory is just a very robust hypothesis that has not been disproven yet. So let's actually define this. Oh, I have it here. So the definition of a theory is the formulation of a robust and apparent relationship among observed phenomena verified by multiple or many experiments. All right, So essentially, when a hypothesis is tested repeatedly and not disproven, then it can become a theory. So you can disprove a theory with just one unpredicted result. And so a theory is essentially just the best idea that agrees with all of the facts known to the community. And like I said before, there's a gray area between hypothesis and theory. It essentially, once a hypothesis is accepted by the scientific community, it can become a theory. So we talked about theories. So how do laws relate to theories? Well, let's just define what a law, a scientific law is. A law is an explicit statement of fact. The biggest difference between a law and a theory is that a law cannot be disproven. Laws come from sets of observations that always seem to hold true. So, for example, the law of gravity. I know if I go anywhere around the world and do the letting go of the pen experiment, right, that the pen will drop. That is the law of gravity in motion, right? Gravity never turns off. It's a law, regardless if you do the experiment, if I do the experiment, it's always there. So, laws are based upon absolute facts. So that's what I mean by irrefutable, that essentially they can't be disproven. Other examples of laws includes the law of conservation of mass, that we never lose mass, or the conservation of energy, we never lose energy. So all of these laws, gravity, mass, energy, all those things, they can never be disproven. They always exist. A law can never just be turned off. All right. So a summary of the scientific method and how it operates. Remember, we essentially take observations that we collect from the world around us. We form a hypothesis that may explain the observations that we see. We can do a bunch of experiments to test that hypothesis, right? So you can do this cycle, hypothesis, experiment, repeat that many, many, many times. And once a hypothesis has been verified a number of times, it can then become a theory. As long as the experiments verify the hypothesis, then it can move on to a theory, as long as it's not disproven. All right. So the last slide here, just summary of chemistry, why you're here, why you're studying chemistry. So this year we will study the composition, structure, properties, and reactions of matter. That is essentially what chemistry is. We're studying these four things in relation to explain the matter that surrounds us in this world. So in this semester, we will use chemistry language to describe these things. So in the next slides, we'll talk about different chemistry vocabulary and how we can collect scientific data to explain the world around us.